Hello, welcome to my short talk or presentation. I'm Matthias. I'm a usable security and privacy researcher at SBA Research, but currently abroad at the Tokyo Institute of Technology. And well, I do work with secure computing, and I'm here to answer the title or the question, what the heck is secure computing and why should I or you or we all maybe care about it? So first, what is secure computing? So basically, it means you compute on encrypted data. And inside of secure computing, there are two different paradigms. One is called secure multi-party computation, where multiple parties or entities, it can be companies, can be people, can be anything, basically anything that's a computer or a server, engages in a protocol, and then together you jointly compute on private data. So imagine everyone has their own database, and you don't want to share the databases or the data in the databases, but you still want to do some statistical analysis or something else. Then you can do that with secure multi-party computation. So basically, you could say it's data sharing without sharing the data. And the second thing, which is also under the umbrella term secure computing, is fully homomorphic encryption. And that's basically a way to outsource computation without losing privacy, and basically works by computing on ciphertext. And I will mostly talk about secure multi-party computation because that's the research area I'm working in, and also because I think it's, in terms of technology adoption and maturity, it's further along the line. So what are the differences between MPC and FHE? So generally, MPC is faster, and you have more tool choice because, as I said, it's more mature. But the downside is you have more communication. So in MPC, you have certain operations, certain things that need all the parties to communicate with each other. So they need to be somehow connected through a network or internet. It can be anything. And fully homomorphic encryption has less communication because let's say you have your data and you want to outsource the computation, then you just encrypt your database, you send it to the cloud provider, and then they do their thing, and you just have to communicate when you return results. But everything else in between doesn't need communication. But the downside is that currently it's still a lot slower, and there's less tool choice. So there's some tools that you can already use. Microsoft has a library, for example, that does not fully, but homomorphic encryption. There's a difference with the operations that you can do. So yeah, there are not as many tools as with MPC. And the difference between those two is that homomorphic encryption is based on mathematical properties of the ciphertext. And you can think of it like you have two plain text values and you multiply them and then encrypt them. You would get the same with homomorphic encryption if you encrypt them first and then multiply the ciphertext. So basically the order of encryption and decryption doesn't matter as much. But I'm not an expert on that, and I will mostly talk, or almost exclusively actually talk about MPC. MPC is based on secret sharing, which is a weird term, like how can you share a secret? What is that? And I will explain that in detail. There are different secret sharing methodologies, and I will explain one of them, which is really easy to understand and shows you that, yes, you can actually compute on data without sharing data. The other thing is oblivious transfer that you can use to create MPC protocols. And that's basically two people or two parties. One has two values and the other one wants to select one of the values. And the idea is that the person selecting the values only gets one and only one, and the person holding the two values doesn't know which one was chosen. How you get from that to multi-party computation is too much for this talk, but that's why I focus on secret sharing. So for a small example, let's say we want to compute the average salary of the academy participants, and we only want to learn the output and nothing else. So our objective really is we have our own data and we don't share this, but all the parties learn the output. So what is the average salary? And we do that through additive secret sharing. So here we have 3 parties with their 3 salaries. Because like Nikki said, I'm in Japan, so I chose fitting pictures. So we have a samurai, a geisha, and a ninja. And all of them have a salary. And what they do is now they do some secret sharing and engage in this MPC protocol using additive secret sharing to compute the average. And we are going through that. So what they first do is they split their input, which is the salary, into 3 shares. Here I chose nice numbers, so you can see they are easy to add up in your head. But in reality, those would be random numbers. So the secret share doesn't tell you anything about the original value. That's why I usually have huge random numbers, because then you completely drown out all the information in the randomness of the secret share. What the parties then do, they engage in this communication I was talking about, and they send the shares to each other. So for example, the samurai at the top, he sends his share S12 to the geisha, and his share S13 to the ninja, and vice versa. So the others send their shares to the respective party. So now everyone holds the secret shares, and what they can do locally is they add up the secret shares they have, and they get intermediary results, T1, T2, and T3. And in this example, and also in reality, this would be just some random numbers. So they don't learn anything from this information, but they have these intermediary results, and they again share their intermediary results with each other. So in the final step, everyone has the intermediary result, and they can sum up those results. And because they know there are three parties, so they don't need to communicate anything, they just divide this final sum by 3. And probably you don't have time now, but if you do all the math, you get the correct result. You get the average salary of all the 3 participants, but no one has ever showed or shared their input data, the set 1, 2, 3. And this is a very, I think, fundamental idea that you can actually work on parts of the information that you have. I see a question, and I will probably do the questions later. So I hope it's still relevant later, because then now I would have to read, and yeah, I just want to go through it. Yeah, so as you can see, it is possible to basically split your information in a way that no one gains any knowledge about the information, and then you can run computations on it, and you can get to some result without divulging information. So I hope this really small example gives you an idea that actually MPC is possible, and operating on secret data or on data that you don't share is possible. So what are the actual use cases? So what can you actually do? And I would divide those use cases into 2 major categories. One is privacy, and the other one is security. And privacy, for example, would be where multiple entities or distrusting parties, can be companies, can be governments, can be whoever. They engage in a protocol, and they can compute something on their data, on their privately owned data. And as you can see, well, you can do operations with data, but you don't give the information away, so you basically have privacy-preserving computation. And the other thing is security. Let's say you are an awesome company, and you really, really care about security. And let's say, I think one of the easiest example would be a certificate authority. And you have an SHM that does all the cryptographic operations, but you're really worried about your cryptographic or your key material. What you can do is you split the key material in parts, and you store those shares of the key on different machines, and can be like different hardware, can be different software. Make it as difficult as possible for an attacker to break into all of the systems. But you can still do all the signing and encryption and whatever operation you have with the keys without ever combining the key back together. So it's very powerful in taking away the single point of failure. It also works with databases. You could split the database, and an attacker compromising one shard of this secret shared database doesn't learn anything. So, but you still could run all the queries and everything you want to do. So what are concrete use cases? For privacy, you could imagine training machine learning models on data that you never have access to. And so let's say you are a some company having a health application, and you need people's let's say fitness data, but people don't really want to share the fitness data. You could still create a system where people can help you train a machine learning model, but they don't have to give you their data. Or financial companies doing credit score computation, and maybe they are not so happy with or cannot legally share data about their clients or financial data. But with MPC, they still can, for example, compute credit scores on like all the participants' data without sharing or violating any policies. And the classic example in probably all of MPC literature in research is health data, where I think with the Corona crisis or Corona thing, it would make perfect sense that, for example, all the hospitals and all the doctors in Austria share patient data, or not really share patient data, but you can analyze all the patient data that's available in Austria without anyone giving away their data. So you're completely compliant with GDPR and whatever policy and law you have, but you can still operate on this data and make statistical analysis or whatever you want. And as I said, for security, it's about system resiliency. So it's really about removing the single point of failure, which, you know, key splitting databases, whatever asset you have and you want to protect, you can split without losing the methods, like the functions that the asset provides to you, or the value the asset provides to you. So now that you have some idea what you could do, what are actually important considerations when you want to implement or use MPC? Generally, when you implement MPC, you can think of MPC as a trusted third party. So any system that you can think about where you need a trusted third party to do whatever it is, like to mediate between two other distrusting parties, you could think of this perfect, trustworthy, and perfectly secure third party, and you design your system and create your system, and in the end, it just have MPC as a drop-in replacement. But when you then actually choose the MPC technology, there are a few questions you have to ask yourself. One of the most important ones is, do you need true multi-party computation, or, for example, is two-party computation okay? In scenarios where, for example, only two parties need to work with each other, two-party computation is preferable because usually it's a lot faster. So there are specialized protocols that are a lot faster than MPC. And as with everything, there are no free lunches. And MPC, of course, also FAG has a performance impact on the system. So it's slower, but MPC is actually surprisingly fast. But it is slower, but two-party computation is even faster than MPC, for example. The next two questions are mostly about the security guarantees you want to fulfill. So you have, let's say, three parties, or more parties, and then you need to decide, okay, how resilient do you want the protocol to be? So are you satisfied with an honest majority, meaning that as long as more than half of the parties are not compromised and honestly follow the protocol, everything is secure? Or do you need super strict security and you want to be secure even within this dishonest majority, meaning that, for example, as long as one party is trustworthy, the protocol will not leak information and will abort. You cannot ensure that the protocol goes through, but you can detect dishonesty, and you can then abort the protocol to ensure the security. And the other question is, what is your adversary model? So do you only care about semi-honest adversaries, which generally I think are more commonly called honest but curious adversaries? So they follow the protocol, they do everything correctly, but with every piece of information, so let's say every secret share they get, they try to infer and read and get as much information as possible. Or do you really want malicious security where participants can completely deviate from the protocol? They can do anything. They can attack other nodes, they can inject messages, can do replay attacks, can do whatever. And there are protocols who are able to detect that and again abort in such a case. And then there's also the question, do you have people in-house who know something about cryptography? Because there are some pitfalls with MPC. So everything that is a sound MPC protocol can actually not be very sensible. So an example would be our average salary case. If you do the same thing with a two-party protocol and you know your own salary and you know the average salary, that's all the information you need to compute the salary of the other person. So while the MPC protocol actually worked, the way that the system was designed leaked information, and that's, for example, something you have to watch out. And the other thing is performance. So because the way the MPC protocols protect against leakage of information, some operations are very costly. One such operation would be array access. An array access, for example, in normal programming language, you have an array and you want to access one index. No problem. But because if a party computing or doing this array access, if the party would know which index you access, this already gives them information. And usually what the frameworks do, they hide this by basically touching every index, which of course is a very costly operation. And what you can do instead is you basically do array multiplication and use a multiplexer to select the correct thing. So you have one array with zeros, except the one element you want to select is 1, and then you multiply them together, and then that's the way you can basically select the element in the array you want. But that's of course something you have to know in order to produce fast code. Of course, the other thing perfectly works fine, but it will be a lot slower, and generally people care about performance. So that's something you have to watch out for. And another very important question, I think, is how open are you to work with research code? Because there are some proprietary platforms and there are some vendors who basically support you and help you with applying MPC. But there are not many right now, and open source tools there are a lot more open source tools, but the downside is, of course, there's less tech support, or sometimes there's no tech support. And most libraries, of course, are research projects or projects from universities, so they don't guarantee anything about, they need to keep liability away, so they have this huge disclaimer like, don't use this in production, blah, blah, blah. And you don't have this problem with proprietary platforms because they sell it. Of course, they are liable for that. So there are the tools I talked about. For proprietary tools, the two biggest ones, and I think the two most relevant ones are Unbound, and they basically exclusively focus on the security model. So they do key splitting and everything that you can do with key splitting. So they also do some, of course, blockchain stuff and HSM and yeah, everything. But the good thing with Unbound and Cybernetica, of course, is that you have a point of contact. So there's one person, usually at least one person responsible for you as a customer, and they help you implement whatever you want to implement. And Cybernetica is more focused on the privacy setting, where they provide ShareMind, which is their framework, their infrastructure, and they have the computing nodes and like the client. You have to write the client software, and then you can do distributed, like secret shared database queries and stuff like that. So that's Cybernetica's approach to the whole thing. And in terms of open source, there are many tools. I can give you a direction later, which there's a really nice paper that it's scientific, but it's not like anything weird. It's a really nice overview about the experience that the researchers had implementing different PET or simple protocols with different frameworks. And I think the two most promising ones there, generally it depends on your security model and everything, which library you want to choose. But for example, if you care about usability, then GIF is a really nice framework. It's written in JavaScript, and it runs basically on everything that can run a web browser, so any mobile thing, any server with Node.js, anything. But of course, you have to deal with JavaScript, and like I said, it's an open source project, so there is no dedicated support for you. I actually use GIF for the project right now, and they have issue tracker on GitHub, and they are really nice and helpful with comments. And so, yeah, it may be slow, but it might be a viable alternative for you. And the other thing, for example, is Scale Mamba, which is a very, very sophisticated framework. It's basically one of the founding fathers of Unbound is also involved, or is leading mind or brain behind Scale Mamba. The setting up the infrastructure is a lot more difficult when compared to GIF, but once you have it up and running, it is like a Python-like language that you can use to do the computations, and it's very powerful and also supports. So it has very good documentation. Actually, both GIF and Scale Mamba have very good documentation, which is unfortunately not a given with the open source projects. That also already brings me to the end of my talk, and I hope you learned you take 3 important things away. One is that secure computation is possible, that yes, you can compute on data that you don't share, and you can do that jointly with other people. You don't even have to trust, you just have to have a common goal. MPC basically can replace trusted third parties if you design the system in a way that basically the trusted third party is completely replaced by the MPC protocol. And lastly, I think MPC can enable very interesting new business cases and also increase your security. Like I said, maybe you're not allowed to share your data with some other entity that you would want to share because you have a common business interest. But with MPC, you can create a system where you both can work together on whatever data you have, but you don't share the data, so you're completely compliant with the policies. Because MPC is very new and people have generally difficulty understanding it or trusting it, because it's very difficult to wrap your head around how you can compute on data you actually never share. Generally, lawyers still want NDAs and things like that. So there have been case studies where the systems were used, but the lawyers still required all the legal stuff. Although it's not necessary because, like I said, you don't divulge any information. And that's the last slide. So because I'm a researcher, I'm doing a study on the adoption of MPC, or probably why there is no adoption. And it's a 30 to 45 minutes interview, which will be recorded. But the recording is only for transcribing the interview for data analysis. And of course, we follow absolutely the GDPR and strict protection of participants' privacy. I'm personally very passionate about privacy, and yeah, so I really care about doing everything by the books. If you're interested in participating and helping with my research, I would be very, very happy if you would join. I mostly I really look for people who have sensitive data in the sense of health data or financial data, and you don't need to divulge anything about your data you have. It's really just about how the systems you make and how MPC might be able to help you. You get 20 euros of an Amazon voucher as a small token of appreciation, because yeah, I'm really glad for any help I can get. And if you want to help, please scan the QR code or follow the link down below if you don't trust QR codes, which I totally understand. Or you can also send me an email, and we can talk from there. Thank you, and I think now we can take the questions.
Perfect. Thanks, Matthias, again, also for the great talk. Yeah, let's head to the first question we're having here. Are these concepts already applied in practice, or are they more of a future thing?
I would say they are, like, if you have if you know the technology adoption curve, I think they are pretty they are definitely not peak yet. So I would say they are where blockchain was maybe a few years ago, and there are projects that really use them. So there was a Danish sugar beet auction was done through MPC, where like the buyers of the beets and the farmers union, they didn't trust each other, so they used MPC to do this auction. They actually did it a few times. And also in collaboration with the university in Boston, or the University of Boston, the city of Boston is running a salary study where basically all companies, or not all, but all the participating companies, which are more than a few hundred, I think, submit, or not submit because there's nothing to submit, but they try to compute analysis of the salary data, where they try to find the gender pay wage gap. So yeah, there are applications where it is used. As I said, Unbound provides HSM and like key splitting services, and of course they sell their stuff. So yes, it is used, but it's really early in the adoption phase.
Other open source project where MPC is implemented for better understanding. So because of the blockchain crowd is very open about doing new stuff. There are some projects that use MPC for that. I'm not sure how familiar the people are with the blockchain stuff, but for example, Zcash, they computed the initial values for their like Genesis block, basically their randomness, through multi-party computation. So that's an example where it was used. And for most of the libraries, for example, GIF has even a tutorial, has really nice documentation, and they have examples where they do different types of computations and really show you how you can use it. So I would say, yeah, there are things out there that they can use. Maybe we can also share after talk a few links. Maybe you have some in your pocket which can be shared, and also in the meetup group, so that the people can take a look at it. Maybe. Perfect. Yeah. Then another question also from my side. Maybe you can tell us what were the biggest roadblocks for you to use this this concept for projects or existing projects.
The biggest roadblocks. So generally documentation, I think, is lacking, except, like I said, GIF. I'm using GIF mostly. I used another one as well, which has really nice documentation. But because I also started to learn this stuff. Like I'm not this super deep nerd, like mathematical guy working on the protocols and like doing the secret sharing mathematics. So for me, I'm very applied. And for me, the most difficult part was probably to wrap my head around this, like how do you set up the secret sharing and how do you then compute on shares? Like in this example I gave before was a really nice toy example, but in reality you want to do something more complex, and then it becomes really really interesting because the libraries are also very new. And for example, I wanted to share an array of whatever, and there was this basically standard case where in the library I used, everyone was sharing with everyone. So everyone was meant as participant in the computation. But generally you can also split roles in the system. And I wanted to split the roles. I wanted to have input parties, which just provide the shares. I wanted to have compute parties, which just do the computation, and someone gets the output. And this splitting of roles, for example, was not intended by the library in the beginning, so I had to work around that. So sometimes the tools are not general enough by default. You can definitely build it yourself, but there is manual building involved.
We hope you enjoyed the talk. We wish you all the best, and have a nice lunch break, and take care. Thanks again.
See you.
Bye.